We had that, x minus 1. And we had to come up with something. You could have done the exact same thing. You could have said, all right, 1 over, 1 over. You could have said, look, I want x squared on the bottom, right? But I know it's going to get squared on the way in, right? So I'm going to take the square root of it. And so if you take the square root of that, push it in and square it, it's just x squared. But what is the square root of x squared? X. So this is really 1 over x. Make sense? All right, so I have to do that here and I have to do that here. And then push it through. Now, I'm not going to give you one like that on a test, and there's nothing like that in the textbook as well. But you asked, so that's how you would deal with something like that. Okay? It's a little more complicated because when you do this distribution, nothing is nice. Like, think about what that would be. That'd be 6x over, on the bottom, this would be on the bottom, right? And I would write that as x to the 2/3 power. And then you'd have to use your properties of exponents. And you'd have to rewrite that as 6 x to the 1/3 power, because you take x to the first and you subtract this power. 1 minus 2/3 is 1/3. So it's a lot of playing with exponents. I like the problem personally. I wish there were problems like that in the textbook, and then I would do them, but I don't want to go outside the scope of the book. I don't think that's that fair.
Is that like calculus 2?
No, that's just, I mean, I think that's something that, I think you get to a point after you get through the calculus sequence where if you saw something like that, it wouldn't be too much of a stretch for you to think this way anymore. Like right now, it's the first time you're seeing it, you're like, whoa, I don't think I'd ever think like that. But later down the road, you know what you're trying to achieve, right? You're trying to achieve that the x squared goes away. So you use whatever algebra you can to make it happen. All right. Let's see what else I want to do here. See if there's any other examples I want to look at here. So what's been the rule of thumb? Infinity over infinity? Highest power on the bottom. Try to kill it off, right? And we've seen in the examples I've given you that when we do that, sometimes we get an answer, a nice answer like 3. Sometimes we get 0, and we even got infinity once, right? So there's no guarantee that your answer is always going to be a certain thing. You just have to work the problem out. All right, now I have carefully avoided something in all the limits I've given you. I've carefully avoided this scenarios. Ooh, squeaky. Limit x goes to infinity of x squared minus x. Okay, so I'm going to put parentheses around this because that's all, I'm taking the limit of the whole thing. So I want you to tell me what happens when x gets really big here. Well, what does that become? Infinitely big. And I am subtracting something infinitely big. If you look at everything we've done, I've never given you anything like this where you had something that's infinitely big minus something infinitely big. It's always been infinitely big plus infinitely big. And nobody has had a problem with that. They've said a big number plus a big number is still a big number, right? But what about a big number minus a big number? Is it 0? How big is that number compared to that number, right? So there's a problem here, okay? We have infinity minus infinity. And that is not 0, okay? That is not 0. It seems like everyone in here seemed comfortable with the idea that infinity over infinity wasn't 1, right? Like no one argued with me about that. Like, no, that should be 1. We all understood that we don't know what this is, right? We have to do something. Well, this is the same idea. Infinity, take away infinity. You don't know, right when you see that, you don't know what's happening. You have to investigate further. Now on your sheets, top left box, do you see infinity minus infinity? Okay, that's another one of these problems. So what does it say you have to do? Algebra or a trick? So we are now on our third thing that requires algebra or trick, right? We've done 0 over 0. We've done infinity over infinity. The approach to these are completely different, right? This, we were doing like factoring, not completing square, difference of squares, conjugate, all that. Here, it was kind of like, let's go after that denominator, let's kill off that highest power, right? Now we have infinity minus infinity. What's the rule of thumb for this? The rule of thumb is to try and turn this into a product. Convert the subtraction to multiplication. Somehow try and turn this into something times something instead of something minus something. And there's another word for that. It's called factoring. When you try and turn a sum or a difference, plus or minuses, into multiplications, it's called factoring. So let's factor this. Do y'all see how I can factor? Just take out an x, right? So pull an x out, and you're left with x minus 1. See, now you have multiplication, right? Instead? Now tell me what's happening. You have a huge number, right? Infinity times, now what is this? What happens there? Infinity take away 1? Still huge, right? This is not something that we have any trouble with. A huge number times a huge number should still be a huge number, right? And so the answer to this would be infinity. It kind of makes sense. I think it makes sense. You tell me, does it make sense to you? That if x gets really big, x squared dominates the x. Like this number is going to get a lot bigger than that number is, right? So this term should dominate that one. So this is a bigger number than that number. So really this isn't going to matter. This is the thing that's in control of the situation. So that heads to infinity. What happens if I switch it around? What if I gave you the problem and I switched it and did x minus x squared? What do you think is going to happen now? Do you still have infinity? Do you still have infinity minus infinity? Yes, you still do, right? So you don't know what's happening yet. But if you factor, you get 1 minus x this time, don't you? So this is headed to where? Infinity times, careful, what's that headed to? 1 take away infinity. What? Negative infinity. You don't see that? It's different. 1 take away infinity is a negative number, and it's huge. So this is negative infinity. And you are multiplying these. A positive times a negative is negative. And so this should become a huge negative number. So this should be negative infinity. Do y'all see it? So this is like linear, and that's quadratic. This quadratic will dominate the linear one. So this negative number is going to dominate this one. And so your answer should be negative infinity. Good? All right, I have another one for you. What's the square root of infinity? Infinity, okay. Cube root of infinity? Still infinity. Subtracting, right? So this is infinity minus infinity, right? So again, we need some algebra right here. We need some algebra. We need some sort of trick, whatever it is. And what have I been doing here? Factoring. Okay, can you factor that though? Who do you think's going to win this battle? Which one of these do you think is bigger? Square root of x or cube root of x? Which one's bigger? As x gets huge. You think square root of x is bigger? I agree. I think square root of x should be bigger. So the answer should be positive infinity. But you need to convince me. So you need to factor. How do you factor this? There's not an x in both terms that's easy to pull out. Anyone know how to factor this? So usually you don't see this in algebra. So I'm going to show you if you haven't seen it. You ready? It's going to be weird. Limit x goes to infinity. And this is a problem that I would expect that you could do. I'm going to convert this. I'll put it in parentheses just so we have it. I'm going to convert that to x to the 1/2 and convert this one to x to the 1/3. Do you all agree that's exactly the same thing? That's what those roots really mean? That you're raising it to a fractional power. We call this rational exponents, and we call this radical notation. So this is radical notation. It's one way we could write it. And this is rational exponents, another way we can write it. And this is actually the way that we prefer in calculus to write things with the powers like that. And you will see why later, why we like that. All right, so I still don't see how I can pull an x out. Because it has to be something they both have, right? It has to be something that they both have in common. So watch. Do you agree? Just tell me if you agree. That's all that's important right here. What did I do? I got a common denominator. I looked at both of the fractions, 1/2 and 1/3. I said, hey, a common denominator between those two would be 6, right? So I rewrote each of these fractions with a 6 on the bottom instead of the 2 and the 3, right? So if I want a 6 here, I have to multiply top and bottom by 3. If I want a 6 here, I have to multiply top and bottom by 2. So that's the same problem, isn't it? But by doing that, now they both have something in common. What they have in common is an x to the 2/6. Let me do it and you'll see. I can pull out of this an x to the 2/6. Now you have to understand what I'm doing here, so let's see if this is true. Let's take care of first the last term. Do you all agree that if I just put a -1 here, that to here gives me that, right? What would I need here, though, to get x to the 3/6? So I need to multiply x times something to get that. 1/6. X to the 1/6. Good. X to the 1/6. Why is it 1/6? What do you do when you multiply that times that? What do you do to the exponents? You add them. And what's 2/6 plus 1/6? 3/6. So have I factored it? Have I pulled something out? Yes? Okay, this is really x to the 1/3. So I'm going to rewrite things here. This is x to the 1/3, which is really the cube root of x. And this is really the 6th root of x minus 1. I'm just kind of rewriting it in a different format so you can see it. Now let x go to infinity. What is the cube root of infinity? Infinity, right? This is multiplication now, right? So this becomes infinite times, and then here, 6th root of infinity. Infinity, take away 1, still infinity, right? So you get infinity times infinity, and infinity times infinity is infinity. So your answer is infinity, which is what we thought it would be because we thought the square root of x would be bigger than the cube root of x. What's more important here, though, is the idea that we know how to factor something like this. Right? You don't see this in algebra, right? You don't see a factoring like this? Not where you have to convert these over. Okay. One more type of problem that I need you to see, and then we'll be done with this section. How are we doing on time? Not time, our schedule for the class. Let me see here. So today is the 26th. Oh, good. We're doing good, but remember we skipped 1.5. So when we come back next time, Tuesday, we will do 1.5, which will be continuity. So it's like these two are switching places. And then we will start next week. Also, we will start with chapter 2. So we finally get to like the heart of what this class is about, which is, well, the heart's the limit, but the real like kind of point of this class, which is derivatives. And then we'll have our first exam on the 9th. So we still have, what, 2 weeks before our exam? So we're on track, is what I'm getting at. All right. Limit x approaches infinity of sine x over x. Would that be 1? What are the conditions we need for it to be 1? Sine junk over junk, right? You need the junk to match. Does the junk match? What's the second condition? The what? It has to go to 0. Does your junk go to 0 here? No. You see, there's a difference. If this was x goes to 0, the answer would be 1. But because we're going to infinity, it's not. Right? Be careful. So let's try and figure out what's happening then. I think the easier part to see is what's happening in the denominator. Where's the denominator headed? Infinity, right? See, we don't have 0 on the bottom. Like last class, we had sine junk over junk. Thing was going to 0, we had 0 of 0. So here we have something different. Now, this is the part that's different. This right here. What is the numerator going to? So think about the sine function. And think about, if I ask you what's happening to that function as you go out to infinity, what are you going to tell me? Is it headed to some particular number? No, right? It keeps oscillating, doesn't it? You can't tell me that the sine function is headed towards 1. Because if I move a little bit further down, it's not going to be at 1 anymore. It's going to come down, then go back up, right? You can't tell me if this is headed to 0, because if I move somewhere else, I'll be somewhere else, right? You can't tell me that's headed to any particular number. It keeps oscillating. Right? So would you agree that the limit on top does not exist? It's not headed to a number, right? It's not headed to infinity. It's not headed to 2. It's not headed to 1. So the limit doesn't exist because it oscillates. Yeah? We have not seen this yet, right? We have not seen something like this before. So how do we deal with something like this? How do we wrap our heads around what this could possibly become then? Right? Because the only thing we know how to deal with right now is 0 over 0. We have some grasp on infinity over infinity, right? We can handle that. We can handle 0 over fixed. We can handle fixed. We can even do fixed over 0, can't we? We can do that as well. What else? Oh, we know how to do infinity minus infinity. Right? We've kind of talked about all these different things so far. We have at least some comfort level with all of these, but we have yet to see a problem like this where on the top we actually don't know what's happening. Like it's not headed to 0 or infinity or anything, right? Well, look on your box, okay? Your box of limit thing that I gave you. On the bottom, what does it say about fixed? What does it say down there? Oh, can I borrow? I say on here, when you're looking at this sheet, here, meaning here on this sheet, fixed means non-zero and or what? Bounded. And or bounded. So when I say something's bounded, I mean it's between something, right? So look at the sine function and think about the sine function. Is it bounded? I'm sorry?
Would it be unbounded?
think about the y values. The y values on the sine function are always between -1 and 1. So do you all agree that the sine function is bounded? Below and above, it is bounded. Yeah? So what your formula sheet or that little cheat sheet is saying is that everywhere on that sheet that you look that you see the number fixed or see the word fixed, you could replace that with a bounded function and everything still holds on that sheet of paper. So really, for our sheet of paper, we are considering this to be bounded, right? And what I mean is that sine of x is always between -1 and 1. We learned that in pre-cal, right? Sine is always between -1 and 1. You can see it on the picture. That's a bounded function, but for us, that's the same as saying fixed over what? Infinity. And what does a fixed over infinity always go to? 0. This goes to 0.